Thank you, Terence. I really want to start by thanking the whole organizing team for letting me speak at this wonderful little workshop. It's been a great pleasure doing this, and we're not quite done yet. So I want to talk about some work I've been doing with Bénédicte Haas, who is in Paris. Technically, this is like the result of a long scale project which took us through multiple papers, and I will tell you the story of what we're talking about, which is scaling limits. Scaling limits, so the general idea, I'm sure everyone more or less knows, you kind of take some large probabilistic random object, and large usually means there's some kind of parameter n tending to infinity, and somehow if we rescale something, divide by the power of n in some sense, we observe some kind of limit. So a favorite example would be a random walk, which when rescaled becomes random motion, and n becomes large. And here we're going to be talking about, is there a pointer? Yes, so multi-type fragmentation trees and Markov branching trees. So I will eventually define both of those terms. But now at the start, we're going to take a long introduction where I may be saying things which a lot of people already know, but it's a very good way of kind of introducing the framework I'm looking at. So instead of Markov branching trees and fragmentation trees, we're going to look at Galton-Watson trees and the CRT. Under two different points of view, we'll soon see what that means. So disclaimer, I guess, Galton-Watson trees, nowadays there's a bit of a push to change the name and call those bien-aimé trees. I agree in principle with this, but mental inertia can really slow things down, so I will say Galton-Watson, but can pretend that I'm saying bien-aimé every time. Okay, so what is a bien-aimé tree? So it's kind of the simplest model of a random evolving population you can find. So each individual has a random number of children, and this number of children is chosen with the same distribution, which I'm going to call Greek letter xi. So we get something like that. So I like drawing my trees from bottom up. So we have an ancestor here. Ancestor has a random number of children, so with probability xi of 1, I chose 1. And then this next person, with probability xi of 3, had 3 children, and so on. This one, 2 children, xi of 2, 0 children, xi of 0, 1 child, xi of 1. Note that I'm really just looking at this tree as a graph. So even though technically I drew it in the plane and there's an order from left to right between these 3 people, we can ignore that. We're really only looking at the graph structure. So there's been a scaling limit result for these things for a while, so it goes back to almost 30 years now with David Aldous, and it goes something like this. First, assume that your tree is critical. So critical means your average number of children for any individual is 1. Nowadays, we may call this thing R0. And here we say we ask it to be 1. On average, you have 1 child. And we want some kind of regularity condition. Here, I want my offspring distribution to have finite variance. So the number of children doesn't vary too widely. Then, so what we want to do, remember at the start I said we want a large object with a parameter n tending to infinity. So here, I just had a random tree. I want to make it large. How do I make it large? I just say I want it to have n vertices. So n individuals total, n vertices in that tree, and I just condition on that. So technically you can't always do that. So technically, you might want to just restrict your set of values a little bit, but that's not a problem at all. So you have your large tree with n vertices, and then something interesting happens. First, view it as a metric space rather than a graph. This is something which is very convenient. So imagine that each edge was actually some kind of line segment with length 1, which is, really what happened when I drew it, since you draw a line between vertices when they're connected. And then what happens is that typical distances inside the tree are of order square root of n. So if you go from one uniformly chosen vertex to another, there's around, the only part between them has a distance which is of order square root of n, and you have this interesting scaling limit result due to Aldous. So take your tree. This means literally divide all the distances by square root of n, then it converges as n tends to infinity to a constant we don't care about times TBR. Now, this theorem looks good, but clearly there's probably two things here that need to be defined. First, what does converging mean here? This is a tree. How does a tree converge to something? And second, what is this limiting object TBR? We'll start by answering the second question. TBR is what we call the Brownian continuum random tree. Often gets abbreviated to just CRT for continuum random tree. And so it's a continuum tree, by which we mean it's a metric space which has tree-like properties. Specifically, it's made of lots of line segments that you stick together and you make sure that there's no loops. And it looks something like this. This is a figure done by Igor Kromchensky, also in Paris. You can see it's a bit of a messy structure, but essentially what's happening is you really just have lots and lots of tiny segments screwed together, and sometimes there's longer parts which do appear. And of course, no cycles. So this is, one of those many strange Brownian geometric objects that can appear as scaling limits of various random, reasonably regular graph objects. So I explained one bit of this equation. What is that? Now, what is converge? There's a thing which we use to actually make metric spaces converge to each other's. It's a topology, rather, it's a good metric, which we call the Gromov-Hausdorff metric. And convenient that Hausdorff is mentioned in this talk, considering where we are. The idea with this metric, so as I said, it's used to make metric spaces converge to others, and the way I like to say it is that your distance between two metric spaces, so say x and y are both metric spaces, the distance will be small if I can kind of draw them one on top of the other and superimpose them so that they look almost the same, and essentially mistakes, so in your drawing, things which are in one but not in the other, are pretty rare, and specifically only occur over lengths which are actually quite small, smaller than epsilon. Okay, so that's Aldous' theorem from 30 years ago, and, oh yeah, before that, I'll just mention this here. There's something called Gromov-Hausdorff-Prokhorov metric, which also includes the uniform measure on the vertices of your tree. That's not something I've mentioned anymore, but technically all the results I mentioned have this hidden behind them as well. Okay, so this theorem. So I want to present two proofs to you today, or two ideas behind proofs. And the first one, Aldous, is mainly for historical reasons and to contrast it with the next one, which will be kind of at the center of what I want to talk about today. So Aldous' proof is uses random walks and excursion theory. So the first thing you do is give your tree a planar embedding. I'm going to do a little bit of a drawing here. So I want to make sure that everyone sees everything. So do tell me if this is too low. So we're going to start with the root, which has three children. This one has 3 children as well. And this one has a sequence like that. Everyone can see? Yeah. So planar embedding means that technically we're going to call this the first, this the second, this the third child of the root, and so on. You're the first, second, and third child here. And then what we do is we do this depth-first search around the tree to essentially take your favorite cat or monkey and ask it to climb around the tree. It's going to do it this way. And then go back. And as we do this depth first climb, search, exploration, we're going to record the heights of the vertices you encounter along the way. So here, technically we're going to get a sequence which would be 0, 1, so 0 for the root, 1 for this person, then 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, then go back to the root, then you have 1, and another go back to the root, and so on. 1, 2, 3, 2, 1, 0. So when you do that, you define a sequence, so you can call it xn of k if you like. It's a nice random sequence, and in fact, it's related enough to random walks that it's going to have an interesting limit. Specifically, what we have is this thing. So if you take your sequence xn, kind of rescale time so that it takes 1 unit of time to go from here to there, and then rescale the values it takes by square root of n, then you converge to a constant we don't care about times e. And e is not Brownian motion, it's the standard Brownian excursion. Essentially what's happening is that this is not really a random walk, but it's all close enough to a random walk which starts at 0 and finishes at 0 and stays positive in the middle. And Brownian excursion is more or less a similar thing with full Brownian motion. And it turns out, if we have this, then we can essentially directly deduce the Gromov-Hausdorff convergence of the tree by some generic abstract things. Essentially, convergence of this contour process is equivalent to, well, implies Gromov-Hausdorff convergence of the tree. And having done it this way, this means that the CRT, the continuum random tree, is really the continuum tree which is in some way encoded by the excursion of Brownian motion as this depth first thing. Okay, so this is how Aldous did this 30 years ago. Not quite, because we weren't using the Gromov-Hausdorff framework back then, but it's fine. Now, what I want to talk about now is a different proof by Bénédicte Haas and Miermont, where they use the idea of fragmentation. And you're going to see it's quite different, but certainly we're going to get the same result. And this uses something that we call the Markov branching property. Okay, I'm going to raise a little bit. So take your tree again. So take your tree of size n, and we let dn be the number, well, the degree of the root inside the tree. So here dn is 3. Technically n was 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to still call it n. So here we have 3. And I'm going to call xn1, xn2, and so on the number of vertices contained in each of the dn subtrees rooted in the first generation. What does this mean? So here, this person had 3 children, and then each of those children has a certain number of descendants. Specifically, here I have 4, here I have 1, and here I have 3. Should be using color, that would probably be better. So if you put them in decreasing order, because this is what we like, we have xn1 equals 4, xn2 equals 3, and xn3 equals 1. And it's kind of natural, but it's worth saying, because this is what we call the Markov branching property. If I condition on knowing this thing, so the value of dn, and especially the value of the xn's, then those 3 subtrees I've put here, they actually become independent. And we know their distribution. So imagine I only know this, and I don't actually know what's happening. Okay, this is terrible. Apologies. Let's go back to water. If I know the values of the xn's, but I don't know what's happening beyond those trees, or beyond the first generation, then I will still know that whatever happens here, here, here is independent, and that I will get 4 vertices total here, 1 vertex total here, and 3 total here. So of course if there's 1, it means you can't have children. If there's 3, well, I'm going to redraw the original, but it could, the distribution is what it is, and it could have any tree structure. Okay, and given that, it kind of gives us all of a sudden a very interesting, different way of looking at this thing. And you could say that this tree is now modeling the progressive splitting of an object which has size n. What do I mean? I mean, what if I put a 9 here, a 4 here, and a 1, and a 3 like this, which discounts the total number of vertices in the tree or in the corresponding subtree, and this 9 kind of split in 3, it's split into 4, 1, and 3, and so on. So this 4 splits into 1, 1, 1, and this 3 splits into 2, which splits into 1. You'll notice you lose 1 unit of mass every time. That's because we're counting each vertex as having its own mass. So now your condition Galton-Watson, you can see it like this. You have a particle which progressively splits. All right, and under this point of view, we're going to see that things are actually quite interesting. And the first thing is that, so we don't exactly have this offspring distribution anymore, but the whole distribution of the tree is encoded by the distribution of those splits. So if I know the rule, which, the distribution which tells me what 9 will split into with what probability, and if I know this for any value of 9, then I will know the distribution of my whole sequence Tn. And if I know the distribution of my whole sequence, then I should know what happens when n's tend to infinity as well. So there's an intuitive principle that any limiting properties of my tree, so this scaling limit by square root 10, should be encoded in the limiting properties of what would I get if not 4, 1, 3, and with what probability. And indeed that's the case, but it turns out that the limiting properties we're interested in are a bit complicated, so I'm going to introduce everything bit by bit. Here's the first bit. So it turns out that xn1 divided by n converges to 1 in distribution. What does that mean? xn1 is the largest child if I have a person which size n which splits. So it might have lots of children, but the largest one, xn1, it will be, wrong notation, this largest person here will be very close to n, because xn1 divided by 1 converges to 1. So the way I like writing it is really, you have n minus little o of n here. And so everyone else, if they exist, is going to be little o of n, and even better, when combined, everyone else is a little o of n. This is what happens when you take one step, one person of size n splitting. And we call this a microscopic split, in the sense that you split, but you don't exactly split. It's more like you shave off tons of little tiny bits and then keep the main bits. And so that's one thing which is good to know. Now, the second thing we would be interested in knowing is what's the probability of a different kind of split. So here's a split where your largest person is smaller than 1 minus epsilon times n. So that's something we're going to call a macroscopic split, because it literally means that you've given epsilon as a fixed number here. You've left a positive fraction of the mass for all the others. Then those things, we know the probability of this should tend to 0 because of the first line. And in fact, it tends to 0 at a speed which is n to the minus 1/2. Here's where the square root n we saw at the start comes back. And so the way you should think about this, so macroscopic splits happen at a rate which is around n to the power minus 1/2. So very rare, probability tending to 0, but at a rate which we're interested in. So what this means really in your tree, so imagine that you start with a person of size n. Imagine you follow the largest child every time. So if you take your first split, you're not going to lose much. You're going to lose it low n. If you take, I'm going to do it horizontally, this way you're going to get more space. So if you start with a person of size n, it has lots of, well, maybe lots of children, but the largest one will be almost the same size. So n minus little o of n, and the next one as well. But if we wait long enough, eventually we'll have something which is around n times 1 minus epsilon. And the idea is that for this to happen, you would have to take around square root of n steps. Okay, so if you need to take around square root of n steps, is this not too low? I could probably raise it as long as we don't need the slides. If you need square root of n steps to see anything actually happen in your tree, then it's understandable that the tree overall has a scale which is square root of n. Okay, and my next equation is just a more precise version of this. So to do that, we need more precise notation. So I'm going to take my sizes. Remember, xn1 is the largest child, this is the second largest child, and so on. We complete it with zeros and rescale the whole thing by n. Then I have this. So ugly equation, but it's not too bad. Let's go through it bit by bit. So first, forget about this limit. Imagine we didn't have the square root 10 on the left, and we were just taking expectation of 1 minus rescaled largest person times the function of the whole vector. This should tend to 0 by the first line I wrote. And then, if I multiply it by square root 10, then more or less by the second line I wrote, this should not tend to 0. This is the blow-up factor you need in order to really essentially identify what happens in a macroscopic split. So some kind of convergence in distributions, more convergence of measures really, and we get a convergence to that. So what is happening here? Essentially, this means that in your macroscopic split, your n will become around nx as the largest child, and n times 1 minus x as the second largest child, and all the others will be negligible, so 0 in the limit. So you end up with some kind of a almost binary split where anyone who is not in the largest two is just very small. And this x is chosen according to this measure nu br, which we don't care much about here, but here's the technical definition. Question.
Just a question. So this small on of the other smaller components, the accumulation effect over square root n many steps, does that actually feed back into this limit as well, or are all these macroscopic jumps completely just comes from that where you shape up?
Yes, I got this question. Let me think a bit. So I think they get actually squashed away. They get completely erased, and the only thing which matters will be the macroscopic jump. Okay. More or less. So the secret thing which is happening here is that this measure does have an infinite mass at 0. So it is a bit complicated. But if you change your offspring distribution just a little bit, as long as you have this same limit, then you'll have the same result, meaning that small splits don't really matter. And one last thing, I guess, you can change the distribution of this for any small n and not change the result at all. Yeah. All right. And so having completely identified what happens to your split of your n, well, not completely, but given the asymptotic result that you want, it turns out that there is a general theorem by the same two people which gives the scalar region.
Yeah, is there a reason why the integral starts exactly at 1/2?
So that's just convenient to say that x is the largest and 1 minus x is the second largest.
Okay.
But it could start at 0. You could do it from 0 to 1 and then put a max and a min here, and it would still be the same thing. Convenient. Okay, I'll mention, since I put it here in red, this is not an easy proof. It takes multiple pages, but essentially it's still about looking at random walks and interesting limiting properties in random walks. So there's still a lot of relation with Aldous' proof. Okay, to finish the introduction, this gives us a different point of view of this continuum random tree from the original proof by Aldous. Here, my Brownian tree is the family tree of what we call the fragmentation process, self-similar fragmentation process, which is, in some sense, a population model where individuals have a thing which you can call the mass, size. The mass is a number between 0 and 1, and each person is going to split in two eventually. Specifically, so if I have mass m, I'm going to split in two. So split into mx and m1 minus x at a certain rate. And the rate is given by this nu br of dx. But also, there's an m to the power minus 1/2, which means that the smaller you are, the faster you split. And this is what guarantees, for example, that your tree is actually finite. So we call this self-similarity. And then there's this typical branching property where if two people are alive at the same time, whatever happens to one and the other is independent. So we call that the branching property. And in some sense, this means that this is more of a non-interacting particle system than an interacting particle system. But we really like branching. All right. So this was things which were done at most 10 years ago. Now let me talk to you about newer things. So specifically with Bénédicte Haas, we kind of devised a general-ish framework under which we can get similar results to this, but with hopefully more applications. And the general framework of what discrete trees, so things like that, we want to have limits of is what we call multi-type Markov branching trees. So we have a bit of an intuition of what Markov branching means. But now let me give you a proper definition and include this multiple type thing. It's actually not that bad, and almost close to what we just saw, but in a discrete setting. So take a population model where individuals reproduce and have children, and each individual has two characteristics. One is size, so we want it to be a positive integer. We can let it be 0 in applications, as you will see. And the other one is their type. Type is just a member of a finite set, so let's just say type 1, type 2, type 3, type k. And I want them to reproduce in a simple branching way with one interesting condition, is that when you have a person with size n, the total size of their offspring is at most n, so we don't gain mass from one generation to the next. Now, technically, to define a model like this, you're going to need a lot of offspring distributions, which are just rules which tell you if I have a person with size n and type I, what's the distribution of their offspring? Their offspring being a vector of sizes and types. And the tree would look something like that. So that's, I like representing my types as geometrical shapes. So here we have two types, which are circles and diamonds. And here we have the ancestor, size 6 type circle, which they have one child, size 6, different type diamond. then this 6 breaks into 3, which is 4, 1, 1, and then this one dies out immediately. This one has one child, which is the same type circle and dies. This 4 splits into 2, and as you can see here, 1 plus 2 is 3, which is less than 4. That sounds like a Tom Lehrer song. Anyway, so as a kind of interesting reminder, in this setting, the size would drop by 1 at every step, at every split, to be more accurate. We don't require this in general. As you can see here, this person conserves, and this split also conserves, and then this one loses mass. Okay, to show you that this setting is reasonably general and useful, I'm going to give you 2 examples of things which fit. The first one is the growth model of trees. So I'm going to show you a simple recursive way of creating a tree sequence. And this will be done through an algorithm which has one parameter essentially, which is one tree, which you can see is called tau. I'm going to use that as a building block. So I learned recently that Greeks don't say tau, they say taf. So I'm going to try saying taf as well, but I'll probably get it wrong a few times. So, take taf to be any rooted tree, it can be random or not. And here's an algorithm to build a sequence of growing trees. We start with T0. T0 is pretty simple. It's the simplest tree you can think of. If you have only one edge and 2 vertices. So we're going to say the one at the bottom is the root, the one at the top is a leaf. And before we go on, I'm going to say that taf is, so we're going to take a tree which is not too simple so that we can see the algorithm in action. This one. So it has 4 vertices and 3 edges. It's a Y. Okay, what's my step of the algorithm? Given Tn, how do I make Tn plus 1? I choose one edge at random, don't have much choice here, and then add a new copy of taf in the middle. So for example, well, not for example, here I don't have any choice. I have something like that. Left or right has no meaning. I'm just making graphs. They don't have any planar embedding or anything. And you'll notice that the original edge was split in 2, as I do want a vertex here. Then choose another edge at random. Maybe it's this one. And then add a new Y shape here. And then choose another edge at random. Maybe it's that one. And we'll stop soon. How about one more here? Okay. So this certainly creates a random sequence of trees. And I claim that this is Markov branching. Well, how obvious is that? Well, you'll see more in the next slide, but the first split is here, right? And essentially it splits into 2 subtrees. And clearly those 2 subtrees are in some sense a smaller version of the original. For the main reason that in each of those 2 subtrees, all I've done is take the same algorithm with fewer steps. So it should be essentially the same thing. But there is a little bit of a multi-type structure hiding behind this. So let's make this clear. So first off, the previous definition that I had a possible split at the root, which is not the case here. So we want to say that all those trees are planted, which is meaning that the real root is this, and we have an extra edge, 4. And then here's my size and type thing. So the size of an individual corresponds to the number of steps that you've taken at it or beyond it in the algorithm. So technically, for example, I've taken total number of steps I've taken was 1, 2, 3, 4. So what would happen is that this person has size 4, this person has size 1, size 2, size 1, and then all the leaves or further things get 0. And the types is a little bit messy, and usually you would need to think a little bit to convince yourself of that. The types correspond to the subtrees of TAF, which are rooted anywhere except at the root. So essentially, if you look at the subtrees, there's only 2 possible subtrees. Either you reroute here, or you reroute at a leaf, in which case you just get 1. So what we're going to say is that this person has a type which is a circle, and this person has these two have a type which is a diamond. The type 1 and type 2. And I'm going to redo my whole construction. That's probably the simplest way. Well, I didn't have to erase it. Sorry. Show you how the types appear. So you originally start, remember, with just that. And here we have a leaf. So technically we have a diamond. And then when you take a step of the algorithm, your new vertex takes the type of what was beyond it. Sorry. So new vertex, and then we have a copy of TAF, which is like this. Then take a step of the algorithm, maybe it's here. New vertex, it will have this circle type, and then new copy of TAF. And so on. So if we take one more here, then this is a diamond, and then here's my white shape with the text. When you do it this way, this will be Markov branching. Here I've taken 3 steps, so we should have 3, 1, 1, and then 0, 0. Okay, so this method of building trees does give you something which is Markov branching. Here is another model which is simpler, thankfully, which also is Markov branching. So this is K-type Galton-Watson trees. So I haven't defined those, I will not, but hopefully you can kind of bridge the gap between things. So each individual has a number of children independently of the others, and that the nature, the number and types of those children will depend on the distribution, which is informed by the type of the father. So, if I take the Galton-Watson tree with K types, and we like notating them by saying the type of the ancestor is I, and to make them big, like we did with the original, we need to condition them on having many vertices, and what really works well is saying I have n vertices of a fixed type, so maybe type 1. And then what happens is that if you do something similar to what we did before, give each vertex a size which is its number of descendants, but descendants of type 1, only the type which counts to the mass, then this turns out to be Markov branching. It works well, it's quite natural. So we have 2 examples of Markov branching trees, and we would be interested in getting scaling limits of those things using the same general principles as I showed you in the introduction. So what would the scaling limit look like? Well, this is not too bad. Scaling limit candidates are what we're going to call multi-type fragmentation trees, and they're really multi-type generalization of the way I described the CRT at the end of the introduction. So we have, so we have those population models where this time things are continuous, time is continuous, and the size, which we call the mass, is back to the interval 0, 1. But people also have a type being member of a finite set. And remember, before we said that a person with size m will split into two individuals. Here we're going to make this a little bit more general. So a person with mass x and type I will split, not necessarily in 2. It can split into, x times 1/5, 1/5, 1/5, 1/5, 1/5, or generally x times a sequence Sn, where Sn is a sequence which adds up to at most 1. And we're going to restrict soon enough this to be actually add up to 1. So those are the masses of its children, and then the types of the children are just a sequence In. this happens similarly to what we had before. There's a measure which shows you the rate at which this happens, and then the rate is also multiplied by x to the minus alpha, where alpha is positive, meaning that we have this self-similarity thing, and that the smaller you are, the faster you split. So this is not super precise, but it actually does completely define your item. And so we have two kind of sets of parameters. One is the alpha, which is the index of self-similarity, and the other one is those measures nu I, which we call dislocation measures. I want to be a bit more specific about those dislocation measures and what they are and what they need to satisfy. So a dislocation measure, it's a measure on a set, which I'm going to call S down arrow with a line on top, overlined. And essentially this is the space of possible children you can have. So it's two sequences. Sn are just positive numbers which add up to 1, and we want them decreasing, and then the INs are just types. And the nth fragment, the nth child has mass Sn, type IN. And those measures, they're allowed to be infinite actually. So you can split at an infinite rate, that's okay. That can be well defined if we have this additional condition here. So this interval condition is a little bit ugly, but essentially it tells you that so you're allowed to have infinite mass, but this infinite mass happens only when the largest child has the same type as its parent, and the largest child is very close to having all the mass. So we're saying that microscopic events are the only events which have like a large mass. And this is technically very much related to the condition for like when is a subordinator well defined? It's when the integral of 1 minimum x is finite. Technically there's a subordinator hiding behind all this which needs to not go to infinity as well. Okay, and I've been trying to avoid mean notation as much as I can, but eventually we do need to write it. So T I alpha nu is the tree where the parent, the initial person, has type I in mass 1, and then the alpha is the index of self-similarity, and the nu j's are those dislocation measures. So we've defined what can be a scaling limit, and at this stage you might be thinking, well, there's a theorem, it's going to be quite clear and easy, just take what was happening before, generalize it to multiple types, and it works. It's not true, and hopefully you'll be convinced that it's a bit more interesting than that. And technically we're going to have two theorems. But before we go into the detail of the theorem, let me give you the general principle of what's happening. Again, a little bit of notation, just a bit. So Tni is my Markov Branching tree. So this should be on the slide. N is the size of the ancestor, and I is the type of the ancestor. And like we did in the first example of the Brownian tree, we're going to look at the first generation. So the children of this ancestor of type N, type I, size N, we're going to call those Xn and Jn exponent I. And again, no, sorry, that's just the largest one. Only care about the largest one for now. And so what happened before was that my largest person had a microscopic split with probability n to the minus 1/2 times some constant depending on this epsilon here. Here we're going to replace half by a general gamma. And if you have this, you would expect, well, in this case, we're going to have a scaling limit if we divide distances by n to the power gamma, which is true, but we want something slightly more interesting. We're going to ask something about the type of my largest individual. And specifically, this is just the heuristic still, I want the probability of it having a different type. So J is different from I, so my largest child has a different type. I want this probability to be of order n to the power vita, Greek pronunciation. And we're going to have different results depending on whether beta and gamma, depending on their relative positions. So we always have a rescale convergence to some kind of continuum tree, but the interesting thing is that if beta and gamma are equal, we call this a critical regime. Then we converge to a general multi-type tree. This is a theorem which could be seen in some way as just a straightforward generalization of the one-type case. But if beta is smaller than gamma, then something interesting happens, and the types vanish in the limit. My limiting tree is monotype. It's still a fragmentation tree, like I defined, but we don't need to talk about types in it at all. And for reasons that you will soon see, we call this the mixing regime. Okay, that's the general idea. Now I can give you our two theorems more precisely. Here's the first one, where we do keep k-type trees at the end. So, take your whole first generation. This is all the first generation, with sizes and types sorted in decreasing order. And as we did before, we rescale the sizes by n. Since they add up to n is a natural scale. And I want this assumption. So another scary integral, but it's like we had before. So essentially some kind of convergence in distribution of the sequence. But I want to see really what happens with the small and the big split. So I multiply by this thing, and I want, if I ignore the n to the power gamma, I want this to tend to 0, which would mean that almost all of the splits are macroscopic, and the largest fragment has the same type as the parent. This is what this indicative function is for. So those are very common, but if we blow this up by n to the power gamma, then we will get information on the microscopic splits, and we have a convergence to a fairly generic integral of the same function against some dislocation measure, ui. And so we had the same before with no types and with the BR here, and then this works. My rescaled multi-type Markov branching tree converges to the multi-type fragmentation tree, and this is, no, so I said exactly what this was. It's the tree with this self-similarity, and the new are those new i's. Okay, so that's one theorem, and let's give first an application of this theorem. So of the two examples I had before, one of them fits under this multi-type convergence framework, and it's this thing, this growth algorithm. So remember, a Tn of taf was obtained by just continually adding copies of taf at a random edge of your tree. And if we call k to be 1 plus its average number of vertices, and remember that this tree can be random, so it doesn't have to be, then it turns out that we do have a scaling limit, and you take the power 1 over k here. So the power 1 over k is actually something you can figure out reasonably simply, see that it's a natural scale for the distances, but our theorem gives us a strong convergence in distribution to a multi-type fragmentation tree with this inductive self-similarity. And in fact, we know a lot about the dislocation measures involved. So how do you split? And it's very much linked to Earn models. Why is that? If you think about this for a second, if you look at your first split here, well, where will the next step of the algorithm go? Will probably go either in this tree or in that tree. It will be more likely to go in a tree in which I've taken more steps. And that's kind of an Earn process. So, not exactly an Earn process, because you kind of break the thing and pick this edge. But very much linked enough that we can write things. And limits of Earn models can be explicit. They're explicit if the number of balls you add every time is deterministic. So if we know the size, if this tree, even when it's random, has a constant size, number of edges, the number of vertices, then we will know the exact dislocation measures. But I won't write it down because it's a bit messy. And finally, so our theorems only give a convergence and distribution of the whole thing. that's because the Markov branching setting doesn't really exploit the fact that those trees are built on top of another. However, it's in fact true that this convergence is almost sure, and other work, completely different work by Stephenson prove that. But it's not something we can do with Markov branching techniques. Okay, second theorem now. So what we call the mixing case. We're going to ask for something which is similar, but a bit different in terms of assumptions. So now, we still ask for, so we still take root of size I and type n, and in this equation, we ignore what happens to the types of the people of the first generation. I'm only looking at their sizes. Then this is the same thing we've seen before. Most splits are microscopic, the microscopic ones, no, the inverse. Most splits are microscopic, so the macroscopic ones happen at rate e to the minus gamma, blow up by this, and you get this nice result. So this only concerns the masses of the children of the first person. And as far as the types go, we're only going to ask for this. So I want the largest child, probability of it switching from type I to type J to be n to the power minus beta times a certain Qij. And this Qij is going to be, in fact, the transition rate matrix of a nice, irreducible, continuous time Markov chain. So what we're going to say, so what we're saying is that if you follow the largest child every time, then you need to wait n to the minus beta to see it change. But if you only look at the moments where it changes, then you recognize an irreducible Markov chain. And then, under this, we have convergence of my large monotype tree, when rescaled by 2 power gamma, to a continuum fragmentation tree, which only has one type. And at this stage, I haven't defined what its offspring distribution is. Only what dislocation measure, it only needs one. And turns out it's very simple. And it's given by this. So nu is an average of different nu i's weighted by the key i's. So nu I was just, it happened here. And then those chi terms are the invariant measure of this matrix that you saw. So the types disappear. They all kind of mix up together and become one combined type, which is a little bit of all of them. And the reason this happens is that if you follow your largest child and wait until it does an actual macroscopic split, then it will have changed types so many times already that it will have mixed in the sense of this underlying Markov chain. And you can't really, it's not worth trying to identify its type. When things add up, it really has an equal contribution from any type. So this theorem is the one I find really unexpected and interesting. And of course it has an application, which is the second example I gave. So take your multi-type Galton-Watson trees, and so they have offspring distribution, psi i's, we want them to be critical and have finite second moments, same thing we had in the one-type case. And so blah blah blah, condition it to have n vertices of type 1, and then just take the root to be type I. Then we have this theorem. Okay, this should be a 21. 2 typos in those slides, but I'll challenge you to find the first one. And so this tree, when rescaled by square root 10, converges to the Brownian continuum random tree. There's the C here, so there's a constant. This was 2 over sigma in the first case, and we do have it explicitly. It's a little bit messy to talk about. And so we're very happy to have this. This theorem was kind of known before. So technically there was a theorem by Miermont alone who did it with the excursion function method. but had it in some sense being weaker because you needed exponential moments as an assumption. So we have a stronger theorem. This is, there's no doubt in my mind, this is the true condition for this convergence. All right, so that's the end of what the results I wanted to present. And here's a few further questions or things I want to remark. First is, can we get just more extensions of this Galton-Watson result? So things I am interested in is different conditionings. So what we were saying is that we were making a tree big by saying it has n vertices of type 1. You can make the tree big other ways. You can say it has a large height. You can say it has n vertices at all. And all of those things are interesting, but are harder to look at in this Markov branching framework. But still, I think some things can be done here. Other things we could do is what happens in the case of infinite variance. It's known in the one-type case that there's such a thing as a stable tree, which is obtained when you have different conditions on your optimal distribution. That's really, really hard in the multi-type Markov branching world, so not there yet. And this is the part where you come in. I'm interested in any application of this, because the framework is quite general. I feel it's quite general, but I feel also that we haven't found that many examples which are interesting and fit under it. So certainly we would be interested in any idea anyone has about this. And finally, I mentioned that some of this work can be done also with what we call growth fragmentation processes, which are quite a bit more complicated things, where you're allowed to not just split, but to grow a little bit before you split. And there's a bit of work which has been done in the single type case. And that's all for me. Thank you for listening.